Hello and welcome back to our course on drone surveying. Today we will learn about creation of DEM and orthophoto from drone imagery. So let's start with a motivating example. Let's consider Bengaluru, which is a very rapidly urbanizing metropolitan city. So its municipal authority needs to update its base map to meet the rising traffic demands. And one 8-lane ring road is proposed to meet that, and a feasibility report is required. However, the exact road siting and alignment as per the topography, as well as the land acquisition which will take place for that ring road, is unknown. So, how can we speed up the survey for feasibility report? So, as you saw in the feasibility report, we will fundamentally require to have a topography map, and we will also require to have a orthomosaic so that we can understand what is the alignment, and we can also understand what is spread of property on the ground. So, how can we use drone imagery to provide actionable DEM and orthomosaic to provide the feasibility report? So, today we will learn about the difference between drone imagery and a map. What is the processing flow of drone imagery? How do we go about geotagging images? How do we generate point cloud and georeference them using GCP? And how do we get DEM and orthomosaic image from the point cloud? So, let us start with a very classic question in photogrammetry, which is how is an image different from a map? And this is important because we want to generate a map from an image. So, on the left side there is an image, and on the right side there is an ortho image which is equivalent to a map. Now, as you can see here in both the images, there is a courtyard in the ortho image which is perfectly rectangle, but in the image on the left, the courtyard shown in the red color is not rectangle, it is more of a trapezoid. And I know from my personal experience that this courtyard is actually a rectangle. Then we also have the roads. So, in the ortho image, all the roads are parallel to each other, whereas in the image, the roads seem to be converging towards certain point. So, I also again know from my experience of living here that these roads shown in yellow color, they are all parallel to each other, they are not converging somewhere. So, basically we can see that an image differs from a map in terms of the projection. An image has a perspective projection, while an ortho image has an orthographic projection. They also differ in terms of the uniformity of scale. For example, in the image you can see the front of that white building is wider than the back of the white building, while in the ortho image both the front and the back of the white building, they are of the same length. That means the scale is preserved in ortho image, but it is different in the image, as well as they differ in terms of the coordinate reference system. The image does not have a geographical coordinate reference system, while an ortho image does have a coordinate reference system. Based on these, we can say an image is unsuitable for direct planimetric measurements, while a map is suitable for finding out the accurate planimetric positions which are true to scale measurement. So, our goal is to generate a map with the help of images. In addition to these, the images also suffer from relief displacement. For example, you can see on the left side that the top and the bottom of the building, the top and the bottom of the pillars of those buildings, they are not aligned, they are not superimposed on top of each other. In fact, the top appears to have been displaced away from the bottom. In fact, if the building has vertical pillars, which I know that this building really has vertical pillars, then in that case, there must not be any displacement of the top with respect to the bottom. And the figure on the right helps us understand why this is happening. So, there are two objects, tall objects A and D, and we can see that when viewed in the photograph from this perspective center, so when they are projected on the photograph, then this top point appears here, while the bottom point appears here, and there is a displacement between the two. Similarly, for the object D also, and this is known as relief displacement. So, the magnitude of relief displacement for a vertical feature of height h is a function of its image radial distance from the principal point r and the flying height above the object's base h. So, we have this object of height h, and it is situated at a distance capital D from the nadir point, and this object H produces a relief displacement of small d, and the image of object H, the top of the object H, is situated at a distance of small r from the principal point, and this image is acquired from a camera which is flying at a flying height of capital H. So, the relationship between the displacement, the relief displacement d, is with r, h and h is d is equal to r into the height of the object divided by the flying height. And we can see here that if h becomes high, that if we have more flying height, then the relief displacement decreases. Also we can see if an object itself is very tall, then the relief displacement will increase. So, in order to convert a set of images or an image into a map, we need to remove the relief displacement as well as the perspective distortion. And this process of removing the relief displacement and perspective distortion from individual image is known as orthorectification. It uses a 3D digital surface model to reposition every image pixel to its correct geographic coordinate, hence creating a single orthophoto. So, let us look at this setup. Again, image is acquired from the perspective center. We have terrain, we have several points on the terrain shown in blue color, and we have a building on top of the terrain which is shown in red color. And this terrain is imaged in the image plane. First of all, we can see relief displacement. For example, this blue point and this red point, they are on top of each other, but in the image they appear displaced with respect to each other. At the same time, we can also see that this very far away point, this blue point and this point on the building, this red point, even though they are very far, they appear very close to each other. At the same time, there are a lot of points which are on the terrain, but they are completely hidden in the image because of the building. So, assuming we have the image and assuming we also have the terrain, then based on the terrain, every image can be reprojected back onto a flat 2D surface, and this repositioning every image pixel to its correct geographic coordinate is known as orthorectification, and this leads to a orthophoto. And because a single drone photo only covers a small area, then by stitching hundreds or thousands of individually corrected orthophotos together, a large and seamless orthomosaic map is created. So, how do we go about it? So, we need primarily three set of data sets. We need raw drone images which may lack positional information and geodetic coordinates. We need GNSS log from the ground, from the base. So, it can be from the ground station which you have established, or it can be from a coarse GNSS data. So, we need their GNSS logs, as well as we need the navigation file from GNSS. So, it is a GNSS broadcast ephemeris data file which has information about what is the location of each satellite, what are the errors in the atomic clock, and so on. And the other GNSS log we need is from the drone, which acts as a rover. So, from the drone GNSS, it can be a RTK log if you have a RTK drone, or it can also be a single point GNSS observation, which can then be processed using the PPK. And apart from that, we also need from GNSS the timestamps, which are the click event logs, which can be used to synchronize the images with the GNSS positions. They are also known as click logs. In addition to this, the third data set that we need is the ground control points, and these are high precision survey coordinates which are pre-established on the ground. So, creating an orthomosaic from the drone images, it has two major phases. In the first phase, using overlapping images, a collection of data points with the known 3D coordinates and RGB intensity is generated, and this collection of data points is known as point cloud, and it can represent either a surface or an object. And the second phase, from the point cloud, we generate digital elevation model, digital surface model, digital terrain model, as well as orthomosaic image. So, now first let us understand about the first phase. So, in the first phase, using the overlapping images, we will generate a dense point cloud, and this happens through geotagging those images, finding out what are the key points or what are the notable features in that images, and then finding out the matching between the notable point, matching between the key points in the overlapping portion of the images, and then using the matched key points to perform structure from motion bundle adjustment, wherein each image is relatively oriented with respect to each other, and based on that the ground coordinates, the 3D coordinates of those key points are established. Then those 3D coordinates of the key points are georeferenced with the help of the ground control point, which leads to a georeferenced sparse point cloud. Then this georeferenced sparse point cloud is densified through multi-view stereo algorithm, which leads to a georeferenced dense point cloud. So first let's start with geotagging. So in geotagging, using the photo timestamps, corresponding drone coordinates are assigned to the metadata of each image. So this shows an example of geotagging where we provide the software. In this case it is Emlet Studio software. So we provide the software with the GNSS log of the drone, GNSS log of the base, as well as the navigation file, and based on this the corrected flight path is generated. Now based on the corrected flight path, it is combined with the timestamp of the images to find out what is the coordinate at which the image was acquired. So basically this is the process of geotagging the drone image. So through this the images have been geotagged, and once if we check the properties of the image, we will see that every image has latitude, longitude and altitude information. After geotagging, it brings us to key point detection, wherein it identifies notable features such as corners or intersection or sharp pixels in individual images, and this is done using algorithms such as SIFT, which is scale invariant feature transform. So you can see on the left image we have a mountain, an image of mountain, and there are some notable features. Maybe there are some sharp features, there are some intersection, there are sudden change in the variation of the snow and the background soil, which leads us to identification of key points. So we can see the key points which are present in this image, which has been done using the SIFT algorithm. Now key points are detected on individual images, then key point matching takes place on a pairwise images. So this shows an example where there are two images with certain overlapping portions. So you can see that this portion is overlapping between the two images and corresponding key points are matched. So for example, this key point matches with this key point over here, all these key points match with these key points, all these key points match over here, and so on. So in this incorrect matching, if there is any incorrect matching, they are filtered out and only best fit matches are considered. So algorithms such as RANSAC, which stands for Random Sample Consensus, and ANN or Artificial Neural Network are used to achieve this corresponding key point matching. After the key points have been matched, then structure from motion bundle adjustment takes place. So this process uses the corresponding key points across the image set to calculate the exterior orientation parameters, also known as the 3D pose of each image, and using the bundle block adjustment, the 3D pose and the 3D point locations are further refined simultaneously to minimize the reprojection error. Let's look at it in a slightly bit more detail. So this shows the setup of structure from motion. From the drone, we will only get images I plus 1, I plus 2, I plus 3 and so on. And in those images, so far we have been able to map the corresponding key points. So for example, those key points are P1 and P2. So we can see P1 and P2 because they are corresponding key point in all these images. So from the structure from motion bundle block adjustment, the algorithm calculates the camera pose, which is in the form of capital XYZ and omega phi kappa, basically the coordinates of the camera as well as the roll pitch yaw of the camera, as well as it also calculates the coordinates of the ground point, and this is done by triangulation process. Then the bundle adjustment optimization takes place that simultaneously refines these positions of the camera as well as the orientation of the camera, as well as it refines the 3D position of the point locations by minimizing the reprojection error. And the reprojection error is the difference between where the 3D points are projected in images and where they are actually observed. So using the bundle block adjustment, first for example we have P1, P2. First for example this camera or pose is estimated. Then based on the camera pose, the ground position is estimated, and then based on the ground position of this P2, again we estimate where it occurs in the image. So if this projection of the ground point on the image matches with the actual position of that point in the image, then we can say reprojection error has been minimized. Otherwise, it has a high reprojection error. So structure from motion essentially leads to a relatively oriented image. So it performs not an absolute orientation, performs a relative orientation. All images are relatively oriented with respect to each other. So this shows an example of image alignment using structure from motion, and you can see these images in the white color. Also on the right side you can see the image orientation, and you can see how those images are oriented with respect to each other. In this, maybe drone was going like that, and for all these images drone was going towards right, and again for this drone was going towards the left. And the sparse point cloud possesses correct relative orientation, but it lacks absolute scale and georeferencing. Why? Because so far we have not used any geo coordinate information. So far we have only used the information of the key points and their positions in the images. So how do we overcome this? So we can overcome this by including the camera locations from the geotagged image either during the SFM bundle adjustment or immediately following that. This will lead to a georeferenced sparse point cloud. To further improve the georeferencing of the SFM point cloud, GCPs are used, and GCP location must be visually identifiable in the images, and their position must be known to survey grade accuracy to achieve that. So using GCP, we can get improved estimation of interior orientation parameters as well, such as focal length, principal point and lens, radial and tangential distortion. And finally, by including both the geotag information as well as the GCP, it will lead to accurately georeferenced sparse point cloud. So this shows an example of the GCP which is present over here on the right side, and the coordinates of the GCP are also imported into the project. So coordinates of the 5 GCP are shown here in easting, northing and elevation, and center of each GCP is manually identified and tagged in all photos where it is clearly visible. This action establishes a direct link between the highly precise survey coordinates and their corresponding image pixels. Then following GCP integration, the relative orientation of all images is refined again through a rigorous least square adjustment. So through the bundle block adjustment, the software reruns and optimizes the alignment calculation. It scales, rotates and shifts the entire model to minimize the reprojection error between the calculated GCP positions and their true surveyed coordinates. And this results in the sparse point cloud becoming fully georeferenced. So every point is now defined within a real world coordinate system. And an accuracy report can also be generated now to verify the root mean square error on all control points. Now let's look at one such calibration report. So this shows interior orientation parameter which have been calibrated with the help of ground control point. So there is focal length, there is principal points in the x and y direction, there are the radial distortion coefficients, there are tangential distortion coefficient. And before the GCPs were integrated, you can see all these coefficients were 0, except focal length, all the principal point was also assumed to be 0. But after we integrated the GCP, it was calculated with this algorithm, their values. So now we know where is the exact principal point. We know the focal length is not exactly 4000 pixel, it is 4047 pixel, close to that. And we also calculated the values of the lens distortion coefficient. Based on this, the positions of all the ground position of all the points in the cloud was refined. So Here we can also compare the refined position with the actual ground position. So this shows the ground control point coordinates which are estimated using GNSS, and on the other side we have the positions estimated using the refined point cloud, and we can see there is very small distance between the refined point cloud as well as the actual position on the ground, and this distance is within 2 millimeter for most cases. Root mean square between the x, y, z and the calibrated x, y and z coordinate is also within 1 millimeter in all the cases. That means the use of ground control point is very much paramount in improving the survey accuracy. So now this shows the sparse point cloud which is generated using the structure from motion and georeferenced using the GCP. So these are all point clouds. Now it should be stated that a sparse point cloud, as we just saw earlier, this is called sparse because it only consists of correctly matched key points. The number of such key points is quite less, and that leads to the sparseness of the point cloud. As the final step, a multi-view stereo densification process is also performed. Using this, a dense georeference point cloud can be generated, and the multi-view stereo point densities are at least 2 orders of magnitude higher than structure from motion sparse point cloud. This makes the multi-view stereo point cloud comparable to the LiDAR point cloud in terms of density. So in the multi-view stereo process, 3D coordinates for every pixel across overlapping images are calculated by transforming the sparse framework into a detailed and textured model. This results in a high density photorealistic dense point cloud. So this is what we get after this, a georeferenced dense point cloud. So if this was the sparse point cloud that we had achieved earlier using only key points, then this is the dense point cloud which is achieved after densification with multi-view stereo. Now analyzing a point cloud directly is very computationally demanding, as well as many geospatial applications require data in raster format rather than the point cloud. For example, digital elevation model and orthophoto and orthomosaic. Further, several hydrological modeling applications also need a DEM raster. So how do we generate these data sets? That brings us to the second phase, where we use the georeference point cloud and use that to generate digital surface model and orthophoto. So from the georeferenced point cloud, first of all we perform filtering. We filter out which are the ground points and which are the non-ground points. So these are the ground points, and points above are non-ground points. So we identify that. Once we are able to identify that, we remove all the non-ground points and then interpolate whatever hole is left behind, and that leads to a digital terrain model. So these are some terms which I am sure you must be aware. This is the digital elevation model, a general term for elevation data raster. There is digital surface model, which is elevation model of the top of all surface feature like building and trees. There is digital terrain model, which is the elevation of bare earth created by digitally removing all buildings and vegetation from the DSM. So for example, if this is how the DSM appears, it's on a slope and there are two buildings. So first the algorithms are used to classify which are the ground and non-ground points. So for example, these are all the non-ground points. Then all these non-ground points are removed, and after that you can see there are some holes which remain. Then these holes are interpolated. After the interpolation of these holes, that leads us to the digital terrain model. So this example shows the digital surface model which is created from the point cloud. Then from the digital surface model, by using an algorithm in the photogrammetry software, we can identify which are the ground points which are shown in the orange color. So all the ground pixels have been classified and identified using Reality Scan's AI classification module. Then the non-ground points are removed and the ground points are interpolated to create a smooth surface, and this is a digital terrain model over IIT Roorkee. Now, how do we generate Orthomosaic from this? So, photogrammetry softwares then use collinearity equation to project each image onto the DSM to remove perspective and relief displacement using the exterior orientation and interior orientation camera parameter. So, we have at this stage we have the images and we have the digital surface model, and then based on the collinearity equation these points are projected onto the ground, where they will appear if they are projected on the ground. So, where orthophoto which is generated through this process, and by seamlessly blending all the orthophotos or also known as orthorectified images, it can be converted into a single continuous orthomosaic. So, this for example shows an orthomosaic over IIT Roorkee, and you can see there is no relief displacement or there is no perspective projection over this area, over orthomosaic image. So, what are the applications of generating these products using drone imagery? So, that depends on whether our goal is to utilize the two-dimensional information or the three-dimensional information. For example, in certain applications, we are more interested in two-dimensional information. In agricultural decision making, such as calculating the crop area, or in the Swamitva Yojana, the stress was to map the boundaries of the field. So, there the stress was on two-dimensional mapping. Similarly, on doing a detailed land cover change or creating master plans under the Amrut scheme, again the stress is on creating orthomosaic because we are more interested in the two-dimensional information. However, in other applications such as ecosystem modeling of canopy height, where we are interested in the height of the trees and what is the biomass that may be stored in that tree, then we are more interested in the height information. Thus, we are more interested in creating a digital surface model. Or for example, in also doing a flood modeling, we are interested in doing a stream bathymetry modeling. In that case also, we are interested in the height information which can be achieved using the digital surface model. Recently, many states in India have been facing problem of landslides. So, in disaster studies also digital surface model are proving very critical. In addition to this, for heritage site documentation as well as for archaeological site, where we want to map the depth information, where we also want to map the height information, again we are interested in creating very high resolution digital surface model. So, in summary, we have understood the distortions that differentiate an image from a map. We understood that by relatively aligning the images, a sparse point cloud can be generated, and then GCPs can be used to accurately georeference it and then finally generate a dense point cloud. And we also understood that we can use the dense point cloud to construct an digital elevation model, generate bare earth model, or we can also generate a orthomosaic using this. So, thank you very much for this attending today's lecture, and we will meet in the next lecture.